Okay, next we have Francesca Rossi, who there's too much to say about Francesca. She's an IBM fellow, the IBM AI Ethics Global Leader, and among other things, many other things, she is president of Triple AI, board director of the Partnership on AI, and a member of the European Commission high-level expert group on AI. And she's known for her outstanding work in constraint reasoning, group decision-making, and AI ethics. Over to you, Francesca.
Thank you, Alex. Okay, let me share my screen. Okay, so during this talk, I would like to focus on a general, general part of the talk to describe my architecture that we use and we have built in our project that is called SOFI, which is inspired by the thinking fast and slow theory of human decision making, and then how this architecture can help in putting together neuro and symbolic approaches, especially in the area of planning. So the thinking fast and slow, or system 1 and system 2, is a very well-known theory of human decision making that has been described, for example, in this widely read book by Daniel Kahneman called exactly this, Thinking Fast and Slow. And according to this theory, human beings use these two broad modalities. Of course, there are many hybrid between the two, but two broad modalities for making decision. One is the thinking fast, also called system 1, which we use every time we make our very simple and cognitively easy everyday decisions. So we make decisions almost in an unconscious way, very fast, very automatic and reactive way. And we use it basically 90 or 95% of the time. So whenever we think that, whenever the decision is something that comes very easy to us. When instead we feel that the decision requires some more attention, then we use the so-called thinking slow modality, also called system 2, which is usually slower, very conscious and deliberate, and it requires our full attention. So we cannot do other things when we are thinking slow in order to decide on a very complex decision. So these two modalities over time, they also interact with each other. So at every single time we make the decision whether to use system 1 or system 2 or thinking fast and slow to solve the current problem instance. But over time, when we become more and more familiar with the problem, we tend to go from initially using mostly our thinking slow modality to more and more using the thinking fast modality. For example, when we learn how to drive or how to read in our language, at the beginning we are very slow and careful and deliberate and requires a lot of resources and attention, but over time we do it almost automatically. So we have this skill learning in human beings where we internalize what we learn about solving a problem with experience, moving from system 2 to system 1. Okay, so the idea here is to be inspired by this theory that in some sense is kind of analogous to a symbolic, logic-based and careful approach to solving problems in AI, compared, which is analogous kind of the thinking slow approach, compared to a experience-based, data-driven approach and reactive approach to solving problem in AI, which can be analogous to thinking fast. So how do we put the two things together in an AI architecture that can leverage both these modalities? So we did it in a very simple way by defining what we call the SOFI architecture, that is a multi-agent architecture with two kinds of so-called solvers, so agents that can solve problem instances. Some are the so-called fast solvers. It doesn't mean that they are fast necessarily, but it just means that they are inspired by the fast thinking modality of this thinking fast and slow theory. So the fast solvers solve problem instances just based on experience and not reasoning about the problem, while the slow solvers are solvers that are using a logic-based approach and symbolic usually approach to solve problem instances, and they reason about the problem instance that has to be solved. So fast solvers can activate independently of anything, of any other agent, so in a reactive mode, just like our thinking fast modality, while slow solvers can be used only when they are deliberately called by the metacognitive agent, which is this yellow part here. So the metacognitive agent has three different roles, may have these three different roles. One is the so-called real-time metacognition that basically decides whether if the fast solver way of solving an instance is good enough, or whether there is the opportunity to better call a slow solver to solve that problem instance. So it's acting in real time when a problem instance needs to be solved. The second modality is the reflective metacognition that reflects, when there is no problem to be solved, reflects upon the past behavior of solving problems and what has been done and whether it would have been better to do something different. And according to this reflection, which usually is a counterfactual reflection, so what would have happened if I had solved the problem in this different way, then it adjusts the metacognition parameters. And the third one is the learning metacognition that updates the models, these green models that you see of that are basically repository of the decision that have been made over time, particularly the model of self, and updates them with the various decisions that have been made, who made the decisions, what the reward was, and the feedback, what those decisions, and so on. And because of these updates, also updates the fast solvers that are relying on that repository of past experience. So notice that this architecture takes inspiration by how supposedly our mind works, not the brain, meaning that we're not saying that the brain has these four or more different categories of components interacting with each other in this way. We are just taking inspiration from how we make decisions using these two broad modalities. It's also a way to combine possibly existing solvers that are based on relying on experience, or that are more symbolic and logic based, that are existing already in AI. And this provides a way to combine them together without having every time to achieve an ad hoc combination given the specific problems that needs to be solved. The metacognitive agent will do this, will help us doing this combination every time there is an instance coming in. So again, this is one of the goals, really, to leverage existing solvers and use them to adapt to their competencies and capabilities in solving problems, but also to make superior decisions, no matter what the criteria are for evaluating a decision, than each one of the two solvers independently. The goal is also to check whether the SOFI instances can improve over time or in the quality of the decisions, and then whether it has this emerging behavior that I mentioned in human beings to internalize these skills, to over time use less and less the system 2 or slow solvers and more the system 1 or fast solvers. So the one instance that I wanted to mostly focus on in this talk is the symbolic planning. So here this is a very well-studied domain for sequential problem solving in AI, where you have an initial state in a world where there are many different states that can, there is a transition function to pass from one state to the another one given by the allowed actions. So here, for example, you see an example of symbolic planning where you are in the blocks world, where there is a table and blocks of different colors over the table that can be stacked on top of each other. And the initial state has this block 3 and block 1, which are on the table, and block 2 on top of block 1. And you suppose you want to reach a goal state, and the goal state has a certain specification. For example, this one that you see here, block 2 on top of block 3, on top of block 1, on top of the table. And the plan that you are requiring for the machine, given the initial and the goal state and the allowed action, is just a sequence of actions applied to specific blocks. So, for example, here the plan says that the first action is unstacking block 2 from block 1. So you take the green and you go to the table that is representing one transition in this world model, and then the second one, and so on. And this is a valid plan because at the end of this sequence of 6 actions over the blocks, you get the goal state. So the idea is that you want to give to this machine a problem instance described in a very well-known language, PDDL, which is a formal language to describe planning problems and planning domains. So you describe the domain, the world, the allowed actions, the initial state, the goal state, and then you ask for a valid plan. So here we decided to use SOPHI to solve these kind of problems. And here we have to decide in SOPHI, the first thing is to decide what we're going to use as fast solvers and as slow solvers. So the first thing that we decided, they said, okay, symbolic planning in AI is usually solved with symbolic planners that can always solve the given problem instance with 100% correctness given enough time. So for example, here as a system 2 solvers, we use fast downward, which is well-known planner, always generating a correct plan for the given planning problem instance. And we use that as our system 2 planner and also as a baseline performance to which we will compare the behavior of SOPHI. Then as a system 1 planner, we will use another planner, which I will tell you a little bit later, which is called Transformer, which is basically a planner built on a transformer-based planner built out for fine-tuning a large language model that is already trained on code. So I will tell you a bit more about that. So, and this is a form of a planner, is a planner because it can solve planning problems of the kind that I told you about, but not always it generates a correct plan or valid or optimal plan. It can also generate incorrect or partial plans. Okay. So we will consider 3 versions of SOPHI with these 2 system 1 and system 2 planners. One is plus only the system 2, so fast downward. The other one is Transformer, so the system 1 planner, plus fast downward. And this is basically says that it's a very simple form of metacognition that says, let's see what Transformers is able to do, but if it's not able to give me a correct plan, so if the correctness of the plan of Transformer is equal to 1, so it's 100% correct, then I don't need to call any system 2 planner, so fast downward. Otherwise, I will throw away what Transformer has given me, even if maybe it's a partial plan, but I will throw away, and I will just ask fast downward, so the system 2 planner, to solve the problem from scratch. So this is a very simplified metacognition that just evaluates the plan given by Transformer, and if it's not good, 100% correct, it will call the system 2 planner. The other version instead, Transformer plus LPG times fast downward. So this is using 2 planners on the system 2 side. One is fast downward and one is LPG. LPG is another planner which is capable of generating plans like fast forward, but is also capable of taking as input a partially complete plan and then continue it to generate a complete plan. And so this allows us to have a slightly more complex version of metacognition here, where if the correctness of the plan of transformer is 100%, then no need to call LPG or fast onward. Otherwise, if the correctness of transformer is very, very low, for example, less than 0.3, then this, if it's higher than 0.3, so it is not correct 100%, but it is some notion, some part of the plan, then this partially correct plan is given to LPG, so that LPG can continue it and possibly get the correct plans. Otherwise, if it's really very, very low correctness, less than 0.3, then we call fast on from scratch. So two different versions of SOFI, and we will compare the behavior with fast onward alone. Notice that here the metacognition is very simplified. It does not have these three capabilities that I mentioned before. It only has the one that decides which solver to use, so the real-time metacognition, not reflection and not learning. So the testing environment has looked at 5 different planning domains. They are very well known. They are used at the International Planning Conference, and they're used to test various configurations that we mentioned. So Blockworth, Grieber, Tower Hanoi, and so on. We used 100 problems for each one of these planning domains, so 500 problems in total. And each problem is generated using very widely used generators. For each problem, we put a time limit to solve the problem instance, which is 60 seconds, and we allocate a certain amount of kilobytes for the memory. So let me tell you a little bit more about the S1 planner, the one that I called the transformer. So we decided to use a large language model based planner, fine-tuning a large language model that has already been trained on code. And in particular, we use code T5. And why did we take this code T5 to fine-tune it for planning problems? Because the idea is that code T5 is already trained to trained to be able to handle some structure and to work according to some structure in the text. So code T5 can already handle code, which is another way, similar to planning, to define some structure on the text. So that's why we didn't start from a large language model that it can deal with open domain language, natural language, but we started with the large language model that already had the ability to work with a structured test, in the particular case, code. So we fine-tuned codified on these 500 planning problems. And the idea is that by doing that, we wanted to see whether this was allowing us to solve problems that were not solvable because of time limitations by traditional planners like Fast Onward or others. So first we performed an evaluation of Transformer as a model, given the training and the test data, and as a planner. And we saw the Transformer performs very well, and we will see them also within SOFI, but as a standalone, of course, not always it gives us a correct planner, and not even an optimal planner, even when it's correct, but it has a very good performance in terms of valid plans compared to other Fast Onward, of course, is 100% valid plans, but compared to other Code T5 or large language models. So then we looked at the version of SOFI that I told you about. So the first one is, as I say, SOFI Transformer FD. So either Transformer gives me the correct plan, or I throw away that plan and I call Fast Onward. And this is the blue symbols that you see here. The other one is SOFI Transformer and LPG and plus FD. So which is, if Transformer gives you a good enough plan, then I give it to LPG to continue it and build from the partial plan, build a complete plan. Otherwise, if it's very, very bad, I throw it away and I call plans and I call fast downward. And these are the orange crosses. And then the baseline, as I mentioned, is fast downward alone, which is the green part. So the instances on the x-axis are ordered by the time that it takes by fast downward to solve them. So they are not ordered in chronologically, but they are ordered on the right-hand side. We have the most difficult ones for fast downward. And the most difficult ones that you see that go up to 60 means that fast downward is not able to solve them because it goes above the time limit. And the y-axis, you have the time. So here you see that while fast downward alone, at some point, it cannot really solve the problem anymore in the last, let's say, 150 instances, the most difficult ones. The other two versions of SAFI can do that. With the one which is in the orange crosses, so the one that has this combination of the two system one solver, doesn't not throw away what transformer alone can do. It's the one performs best because it really keeps, even with the most difficult distances, it keeps a very low time. It needs a very low time compared to the blue one, which instead sometimes, if more than the orange one, it goes up to the time limit. So in the next one, you see the time again, but also compared to the solved problems. So here you see fast downward that can solve within the time limitation about 68.8% of the problems with 16 seconds on average. Then you have the second version, Transformer and FD, that can solve 94% of the problems, of which 38% are solved by the System 1 planner, so you don't need to call the System 2 planner, and instead fast downward solves 55%, the rest of the problems. And then the most complex version, which in terms of time is the better one, but not only it is better in terms of the time, because in average it needs 6 seconds instead of 10 or 16, but also because it can solve more problems, although slightly more, by combining the use of S1 and the S2 planners. So overall, it seems that by doing this combination through this very simple metacognitive agent, you can solve more plans and also take less time. Of course, we don't have to hide that in order to build a transformer, you had to get a larger number and fine tune it over planning problems. So I also wanted to mention some other instances that we tried for SOFI very briefly. So one is SOFI for constrained grid navigation. Here SOFI is called every time you are navigating in a grid and you have to make the decision for the next move, where the goal is to build trajectories that go from an initial state to a goal state, avoiding as much as possible the constraints in the grid. And these constraints can be over the moves, left, right, 8 possible moves for each cell, and over possible states. So, and they provide penalties. So the trajectory can accumulate penalties by violating the constraints, and you want to minimize the penalties, so maximize the reward, minimize the time and the length of the trajectory. So here, in this instance, we use S1 solver, which is a very simple supervised learning agent trained just on past trajectories and their reward. And the S2 solver is a specialized for making decisions similar like a human being would do using this human decision-making theory called MDFT. Here you have the 3 levels of metacognition. The real-time one that decides whether system 1 is good enough or you have to call system 2. The reflective one that compares past trajectories with the simulated ones that only use system 2, and if depending on which one was better, it can adjust its parameters. And then the learning one that considers the past trajectories that have been generated and updates the models of cells, the repository of all the trajectories, and also the S1 solvers. We also use very different, not just one S1 solver, but 5 different versions with various degrees of randomness in the decisions of the S1 solver, because we wanted to see whether SO5 could recognize that a system 1 solver may be unreliable and not to be used too much. So
Francesca, can I request you to wrap up in 2 minutes?
yes, thank you. Okay, so here one very briefly here is that over the various criteria, reward, time, and length, SOFI has a better performance than System 2 alone or System 1 alone, which is not even in the picture because it will go really, it will make all the other one collapse. Is also shows the skill learning behavior that I told you, where over time, and the trajectory on the x-axis are chronologically planning or chronologically trajectory, given by SOFI. And so over time, it learns to use less and less of System 2 and more of System 1, which is the orange one. And you'll see this up and down over 25 trajectories because that's the phase between which you have the reflecting metacognition. So every 25 trajectories, the system stops, makes the reflection, a counterfactual reflection, and adjusts the parameters. So that's why you see this behavior that is a bit up and down every 25 trajectories. It also adapts to the capabilities of the System 1 that we provide, using less of System 1 when it's more too random. I also wanted to mention that we are currently working on a human AI collaboration where System 1 and 2 is not only used in the building of the machine, but also in the fact that leveraging the fact that we know that humans are using their System 1 and System 2 in making decisions and using this information in designing the interaction between human and AI. And the last one is this idea that, of course, planning is, in some sense, an easy problem to use System 1 and System 2 because we have a System 2 planners. And so we are trying just to help the System 2 planner by using System 1 methodologies and combining it with the System 2 planner. But there are many problems where we don't have a System 2 solver. And so how do we use SOFI still to improve the capabilities of the only planner that we have, which may be a System 1 solver, and how do we use metacognition and System 2 to solve collateral problems that can help System 1 make better decisions. So thanks for this is, a picture of our website where you can find all our papers, all our code, and I hope the students here that are listening can play with our code or ask any questions and give feedback. Thank you.
Okay, thank you so much, Francesca. Excellent talk. Just a few questions. Are there any interactions between the fast and slow solvers? And I guess that means direct interactions rather than through the metacognition.
So no, there are no interactions. So it's the metacognition that decides what to do with them. But of course, for example, in the planning, in one of the planning configurations that I mentioned, when the metacognition decides to use the LPG System 2 planner, LPG is given in input the partial plan generated by the System 2 planner. So the interaction is always through the metacognition, but there are some content generated by the System 2 planner that can be given as input to the System 2 planner. So but the interaction is true that is always through the metacognition, although this System 1 and System 2 planner can be not necessarily extremely System 1, extremely System 2, like the ones that I used, can have some hybrid form. For example, you can have a System 2 planner where you have some using of some heuristics, which can be thought of System 1 modalities inside the System 2 solver.
One more, how computationally expensive is the transformer usage in comparison to fast downward solver during runtime or inferencing?
Oh, during inference time, that's the time that I showed you. That's the time results that I showed you. But of course, the fast downward doesn't need the training time that instead you need for the code T5 and then the fine tuning of code T5 over planning domain problem instances. So that's hidden in the tables that I showed you are just about the inference time.
Okay, very good. Thank you, Francesca.
Thank you.
Thank you.